Welcome to the Platform Engineering Playbook podcast, where everything you hear is built, reviewed, and improved by AI, by me, and by you, the listener. This show keeps me, and hopefully you, up to speed on the latest in platform engineering, SRE, DevOps, and production engineering. It's a living experiment in how AI can help us track, explain, and discuss the fast-moving world of infrastructure. Every episode is open source. If you've got something to add, correct, or challenge, head to platform-engineering-playbook.com. You'll find all the content and a link to the GitHub repo. Open a pull request, join the conversation, and make the playbook smarter. Let's get into it.
You've built multi-region infrastructure, Aurora replicating, DynamoDB active-active, EKS clusters running, network layer connecting them, observability showing what's happening. But here's the critical question. When US East 1 fails, how do users actually reach US West 2? Your Aurora secondary gets promoted. Your EKS pods are running in the secondary region. Everything is ready. But users are still hitting US East 1 endpoints. Their requests are timing out. Revenue is dropping. The missing piece is DNS. Route53 health checks, failover policies, TTL configuration. This is your control plane for multi-region traffic. Get it right, and failover is transparent. Get it wrong, and your hot warm becomes no warm during actual failures. Today, you're learning how DNS and traffic management actually work in multi-region architectures. Not the marketing promises, the production reality with all the gotchas. By the end of this lesson, you'll know how to configure Route53 health checks that detect failures in under 60 seconds. How failover routing policies work when health checks fail. When to use weighted routing versus latency-based routing versus geolocation. Global Accelerator for Subsecond failover with Anycast IPs. And the DNS pitfalls that cause production outages, TTL caching nightmares, health check false positives, split brain scenarios. Let's start with Route53 fundamentals, because most engineers misunderstand how DNS failover actually works. You create an A record pointing to your US East 1 load balancer. Users resolve your domain, get the US East 1 IP, connect. Simple. But what happens when US East 1 fails? How? With basic DNS, nothing. The A record still points to US East 1. Users keep getting that IP. They try to connect, it times out. DNS doesn't know the endpoint is down. It just returns the configured IP. Route53 health checks solve this. You configure a health check that monitors your US East 1 endpoint. HTTP request every 30 seconds. If 3 consecutive checks fail, Route53 marks it unhealthy. 90 seconds to detect failure. When the primary is marked unhealthy, Route53 starts returning the secondary IP. Users resolve your domain. Get US West 2 IP instead. They connect to the secondary region. Failover complete, but there's latency. 90 seconds to detect failure. Plus DNS TTL. If your TTL is 60 seconds, existing DNS caches don't update for another 60 seconds. Total failover time, 2.5 minutes from detection. This matches the hot-warm 5-minute RTO from episode 2. 1-minute Aurora promotion, 90 seconds health check detection. 60 seconds DNS propagation, remaining time for connection establishment and cache warming. Health check configuration matters. Route53 offers HTTP, HTTPS, TCP health checks. For web applications, use HTTPS checks against a dedicated health endpoint. Don't check your homepage. Check a lightweight endpoint that verifies critical dependencies. Example health endpoint /health returns 200 OK if Aurora is reachable, if the application can connect, if critical services respond. Returns 500 error if anything is broken. This gives you actual application health, not just, is the server responding? Health check frequency. Every 10 seconds costs more than every 30 seconds. For most applications, 30-second checks are sufficient. Faster checks reduce detection time, but increase costs, and can cause false positives from transient network issues. Failure threshold. How many consecutive failures before marking unhealthy? 3 failures at 30-second intervals equals 90 seconds. 2 failures equals 60 seconds but increases false positive risk. Balance detection speed against stability. Now routing policies, because this is where teams make mistakes. Route53 offers 6 routing policies. Failover, weighted, latency-based, geolocation, geoproximity, multivalue. Each solves different problems. Failover routing, primary and secondary records. Health check on primary. When primary fails, return secondary. This is hot-warm pattern. Use when you have one active region and one standby region. Configuration. Create 2 A records with the same name. One marked primary with US East 1 IP and health check. One marked secondary with US West 2 IP, no health check. When primary health check fails, Route53 returns secondary. Weighted routing. Split traffic across multiple regions by percentage. 70% to US East 1, 30% to US West 2. Use for gradual migration or load distribution in hot patterns. Latency-based routing. Route users to lowest latency region. Route53 measures latency from different AWS regions to users globally. User in California gets routed to US West 2. User in Virginia gets US East 1. Use when you want performance optimization, but all regions are active. Geolocation routing. Route based on user's physical location. All European users to EU West 1, regardless of latency. All US users to US East 1. Use for data residency requirements or regional content. Common mistake. Using latency-based routing for hot-warm. Teams think, quote, latency-based will send traffic to the healthy region. Wrong. Latency-based routes to lowest latency region. If US East 1 fails, but is still responding to DNS queries, users still get routed there based on latency. They then fail to connect. Use failover routing for hot-warm, not latency-based. TTL configuration is critical. Time to live tells DNS resolvers how long to cache your answer. 60-second TTL means users, DNS caches refresh every 60 seconds. 5-minute TTL means caches don't refresh for 5 minutes. Lower TTL means faster failover propagation, but higher query volume. 60-second TTL with 1 million users means frequent requeries. Higher cost, more load on Route53. 300-second TTL means slower failover but lower cost. For hot-warm architectures, 60 to 120-second TTL balances failover speed and cost. For hot with health checks on all regions, you can use longer TTL since all regions are always healthy. Real production example. E-commerce site, hot-warm with Route53 failover routing. Primary US East 1, secondary US West 2. Health check every 30 seconds against /health endpoint. 60-second TTL. Black Friday morning. Database issue in US East 1. Application starts returning 500 errors. Route53 health check fails once, twice, 3 times. 90 seconds elapsed. Route53 marks US East 1 unhealthy. New DNS queries return US West-2 IP. Existing caches expire over the next 60 seconds. Total failover time, 2.5 minutes. Revenue loss during those minutes, $80,000. But the alternative, extended outage while manually updating DNS, would have cost millions. Now, Global Accelerator, because DNS-based failover has limitations that Global Accelerator solves. DNS failover depends on TTL. Users cache DNS responses. Even with 60-second TTL, some resolvers ignore it and cache longer. Mobile networks, corporate DNS servers, they cache aggressively. This extends failover time unpredictably. Global Accelerator uses Anycast IPs. You get 2 static IPs that announce from all AWS edge locations globally. Users connect to the nearest edge location. Edge location maintains persistent connections to your healthy endpoints. When US East 1 fails, Global Accelerator detects it via health checks. Edge locations stop routing to US East 1. They route to US West 2 instead. No DNS involved. No TTL wait. Subsecond failover. How it works. You create a Global Accelerator. You add two endpoint groups, US East 1 and US West 2. You configure health checks. Global Accelerator assigns you two Anycast IPs. Users connect to those IPs. Traffic routes through AWS Edge Network to your healthy endpoints. When US East 1 health check fails, the edge locations immediately stop sending traffic there. They send everything to US West 2. Existing TCP connections might drop, but new connections go to the healthy region. Failover time, under 10 seconds. Cost. Global Accelerator charges per accelerator and per gigabyte of data transfer. About $25 per month per accelerator, plus 8 cents per gigabyte. For high-traffic sites where sub-second failover matters, this is worth it. For lower traffic sites where 2-minute DNS failover is acceptable, stick with Route53. When to use Global Accelerator over Route53. You need sub-second failover. You have users with aggressive DNS caching that breaks TTL. You want consistent IPs that don't change during failover. You're serving TCP/UDP protocols where DNS-based failover is clunky. When to stick with Route53. Cost sensitive. 2-minute failover is acceptable for your RTO. HTTP/HTTPS traffic, where DNS failover works well. Common DNS mistakes that break multi-region. Mistake 1. No health checks on failover records. Teams create primary and secondary records but forget to add health checks. When primary fails, Route53 keeps returning it because it doesn't know it's down. Fix. Always attach health checks to failover primary records. Mistake 2. Health checks that don't test real application health. Teams check TCP port 80 is open, server is up, but application is broken. Route53 thinks it's healthy. Users get errors. Fix. Use health endpoints that verify critical dependencies, database connectivity, external API availability, authentication service. Mistake 3. Single health check location. Route53 health checks run from multiple locations by default, but you can configure them to check from specific regions. If you only check from one location, network issues in that location cause false positives. Fix. Use default multi-location health checks unless you have specific regional requirements. Mistake 4. Ignoring DNS resolver caching. Teams set 60-second TTL but expect instant failover. They don't account for resolvers that ignore TTL or have minimum cache times. Mobile networks often cache for 5 to 15 minutes regardless of TTL. Fix. Set expectations correctly. DNS failover is minutes, not seconds. Use Global Accelerator if you need faster. Mistake 5. Split brain during failover. Primary region is partially failed. Some services work, others don't. Health check happens to hit working services, returns healthy, but most user requests hit broken services. Chaos. Fix. Health checks must verify end-to-end flow, not just individual components. Before we wrap up, pause and answer these questions. Question 1. Your hot-warm architecture needs to fail over when US East 1 fails. Should you use failover routing, weighted routing, or latency-based routing? Question 2. You set TTL to 60 seconds. Route53 health check takes 90 seconds to detect failure. How long until all users are fully failed over to secondary region? Question 3. When would you use Global Accelerator instead of Route53 for failover? Take a moment. Answers. Question 1. Failover routing. This is the exact use case for failover routing: primary region with health check, secondary region without. Weighted routing doesn't consider health, it just splits traffic by percentage. Latency-based routing routes to lowest latency, not to healthy region. For hot-warm, always use failover routing. Question 2. About 2.5 to 3 minutes for most users. 90 seconds for health check detection. 60 seconds for DNS cache expiration, plus connection establishment time. Some users with aggressive caching might take longer. This aligns with the 5-minute RTO for hot-warm from episode 2. Question 3. When you need subsecond failover and can't tolerate DNS TTL delays. When you have users behind resolvers with aggressive caching. When you want static IPs that don't change. When cost isn't the primary concern. Global Accelerator costs more than Route53, but delivers faster failover. Let's recap what we covered. First, Route53 health checks detect failures by polling endpoints every 10 to 30 seconds. 3 consecutive failures marks unhealthy, typically 90 seconds detection time. Health checks should verify real application health, not just server uptime. Second, failover routing policy is correct for hot-warm architectures. Primary record with health check, secondary without. When primary fails, Route53 returns secondary IP. Don't use latency-based routing for this. It routes by latency, not health. Third, TTL controls DNS cache duration. 60-second TTL balances failover speed and query cost. Lower TTL means faster propagation, but more queries. Total failover time is health check detection plus TTL expiration. Fourth, Global Accelerator provides subsecond failover using Anycast IPs and edge network routing. Costs more than Route53, but eliminates DNS TTL delays. Use when subsecond failover is required. Fifth, common mistakes. No health checks. Health checks that don't test real application health, ignoring DNS caching behavior, single location checks, split brain scenarios during partial failures. Remember episode 2's hot-warm pattern with 5-minute RTO? The breakdown was 1-minute Aurora promotion, 90 seconds health check detection, 60 seconds DNS propagation, remaining time for connection warming. Now you understand exactly how those 90 seconds and 60 seconds work in Route53. We'll use this DNS configuration in episode 12 when we walk through actual disaster recovery procedures. You'll see how to test failover without affecting production, how to monitor health check status during incidents, and what to do when DNS failover doesn't work as expected. Next time, cost management, optimizing the 7.5 times multiplier. Episodes 1 through 8 gave you the building blocks. Aurora, DynamoDB, EKS, networking, observability, DNS. You know how to build multi-region, but what does it actually cost? You'll learn why multi-region costs 7.5 times more than single region, not the 2 times vendors claim. The hidden cost multipliers, data transfer, replication, redundant compute, higher operational overhead. Cost optimization strategies that cut the multiplier from 7.5 to 4 without sacrificing reliability. When to use reserved capacity versus on-demand. And the make-or-break calculation, is multi-region worth it for your revenue and risk tolerance? WIT, because you can build a technically perfect multi-region architecture that's financially unsustainable. Engineering succeeded, but the business failed. Let's make sure you avoid that. See you in episode 9.
That's it for this episode of the Platform Engineering Playbook podcast. Every topic, transcript, and summary you just heard lives out in the open at platform-engineering-playbook.com, where anyone can suggest updates or add insights through GitHub. If you've got thoughts, fixes, or new ideas, open a PR. And if you enjoyed the episode, rate us on your favorite podcast platform. We're always shooting for 5 stars. While you're there, give the project a star on GitHub. It helps others find and contribute to the Platform Engineering Playbook. This podcast is generated by AI, reviewed by AI, me and you, a community of engineers keeping our craft sharp. Thanks for listening, and see you next time inside the Platform Engineering Playbook.